All right, hey guys, back again. Problem 5, part A, 2 marks. Looking to me like we're going to find maybe a real component and an imaginary component here. So I'm going to go ahead and I'm going to take in part 1, well, in both parts, I'm going to put my answers here. But I'm going to expand this. And I'm going to get a real component and an imaginary component. So I'll get x squared plus 2ixy plus, minus, right, because that'll be I squared, y squared. So that'll be minus y squared. So you can see that my real component would be this, and my imaginary component would be that. So if I have a real component of -5 and an imaginary component of 12, I can see that x squared minus y squared should be equal to -5. And I see that 2xy should be equal to 12. So if 2xy is equal to 12, then xy should be equal to 6. There you go, an easy 2 marks. Part B, 5 marks. Find hence, using that. Now they're requiring you to use that since they use the word hence. Hence find the 2 square roots of -5 plus 12i. So you may not initially see the connection, but if I take something and I square it and I get -5 plus 12i, I've got 2 possible values that I can plug in here, or expressions, such that if I square them, I get this. Therefore, the square root, or 2 roots, square roots of this will equal those 2 possible inputs there. Okay, so I'm going to get 2 different x plus iy values. So I'm going to go ahead and get started here by taking x squared minus y squared and setting it equal to -5, and xy and setting it equal to 6. And what I'm going to do is I'm going to solve over here. I'm going to find an expression for x squared, and then I'm going to plug it in for the x squared in the first expression. So I'm going to square both sides. That'll give me x squared y squared equals 36. So then x squared equals 36 over y squared. Now I'm going to plug that in here for x squared. So that's 36 over y squared minus y squared is equal to -5. Let's do a little solving here. I'm going to multiply through by y squared. That gives me 36 minus y to the 4th is equal to -5y squared. I'm going to bring everything to one side. So I'm going to set 0 equal to y to the 4th minus 5y squared minus 36. I'm going to factor. I'm finding values for y here, you guys. Obviously, you can kind of see where I'm going with it. But the goal is to get a combination of 2 separate real and imaginary components. The imaginary components will be y, and the real components will be x. All right, so if I factor that, I get y squared minus 9 and y squared plus 4. So I won't get real answers for this one, okay? Therefore, that's not going to yield me, if I want x plus iy, I don't want y to be imaginary. I want it to be a real number. So that won't yield me values. So I will get plus or minus 3. So y is going to be plus or minus 3. All right, so what that tells me is if y equals 3, and I plug that into x times y equals 6, then y equals 3 yields x equals 2. So one of our answers in x plus iy form will be 2 plus 3i. That's one of the square roots of negative 5 plus 12i. The other one, y equals negative 3, if I plug that in, it looks like I'm going to get a value of negative 2 for x, and therefore my other square root of negative 5 plus 12i will end up being negative 2 minus 3i. And there are your two answers. Okay. Definitely implied, not explicitly explained there, but obviously there's a connection between part A and part B. Let's move on to part C. For any complex number z, show that the complex conjugate of z squared is equal to z squared, its conjugate. Okay, so let's take, there's two ways to really do this. We could work with rectangular coordinates, x, I, y, and we could work with r e to the I theta. I'm going to go ahead and do the first method, so method 1, which is if z star, that's z star, squared is equal to x minus iy squared, and if I were to expand that, I would get x squared minus 2ixy minus y squared. Okay, and then z squared star. Okay, I should really put this into a form that's nicer. Real minus imaginary. Okay, you can see that as a in that a plus bi form. Okay, so then z squared. Okay, so we're going to take let's nest this, x plus iy squared, and then we're going to take its conjugate. So that would be x squared plus 2ixy plus y squared. Okay. If I were then to take its conjugate, I would get x squared minus 2ixy minus y squared, which again, if I put it into this a plus bi form, I would get, therefore showing that that's true. Method 2, if z equals r e to the I theta, and z star, its complex conjugate, is r e to the negative I theta, okay, then z squared would equal r squared e to the I 2 theta. So z squared star would equal r squared e to the negative I 2 theta. Okay, and then over here, if I took z star squared, I would get r squared e to the negative I 2 theta, and there you have it. Therefore, z star squared is equal to z squared star. Okay, so I would prefer method 2, honestly. I don't know why you wouldn't use that form. It's so much more compact and easier to work with. All right, guys, I'm going to cut it off right there. This problem also has parts D, E, F, G, H, and I, so I'm going to save those for the next video. Hope this made sense. And again, shoot me questions if you got them.